This program I called 0 and A to efficiencies. At this program I compute three-dimensional unit cell in FDTD using numerical FDTD. And the purpose of this program is to do some analysis about the near fields of the of a grading, inner and outer, at the aim target, but in general it can be for any grading. So first I'll speak about the parts of the program and then the code that run it, and afterwards I'll show the post-processing using another program I built in MATLAB. So the material can be built by models that can be found here, but for a complicated model like this, like the grading, for example, one should write a script. Looks something like this. At the script I built models for rectangulars and define its dimensions, and of course the material. The first one here is, as you can see, is photoresist. Other maybe a bit more complicated structures use rings models. Add ring, and these four the following structures. You can see it here, these areas. The model itself is something like, you can see it here, something like 8 micron on 8 micron, and it's one of the commercial models I took. The FDT zone is dedicated only for the unit cell. In the outer case, the unit cell can be framed, and it's supposed to be in 2D because the horizontal and vertical gradings. Let's see the other zone. This is okay. The other zone over here has, of course, a different frame for the FDTD zone because the structure is different. So we need to take in account also this grading in the vertical direction. I won't go into details, but generally saying the simulation time is 40 femtoseconds, and the mesh is with periodic boundary conditions at x and y, of course. You can see it here. And the PML, perfect match layer, will be at z direction. In addition, I built monitors. RS is the space, RG is grading, and it's also the same if I'll jump to zone 2 or realm 2 as I call it. So also here This is RS, and this is RG, and this is RS. There's also another monitor at the whole area, and of course fields at Y direction is to have also the cross section of both gradings. I also add monitor for monitoring the stability of the algorithm. So here and here at the end of the run, we should see the field vanish. So what FDTD does, it transmits a pulse, a narrow pulse of some spectrum that I'm setting in other file, and from that pulse, FDTD see the steady state by inverse transform of the response of the medium to the pulse. So one should take into account the global parameters for the input. In this case, it's 300 nanometers to 700 nanometers, and in time it looks like this. So we have a lot of much time for relaxation, so it's good. And sometimes when you set the parameters here, you should see that you're not overriding the global source settings. If you want to, of course, it's possible just to override the settings. So the run, I'm running it here. The settings for the FDTD is here, and what I'm doing is I'm recording for a range of wavelength what is the energy at the near field here at the grading and at the space. Let me run just one time to show you what angles I'm running. So let's take this realm. Okay, so the MATLAB code will get the solution for zero NA illumination at X direction, 45 direction, and Y direction. And this is a basic run to understand how the gratings behave in sense of polarization. Later on, I will extend it to some NA not equal 0, and but when we'll get there, you'll see it's a bit more complicated. So let's say I have some solution. Before the solutions, let me show you the parts. So the part is running the program at realm 1 or realm 2. It's the outer or the inner grading.